So the mission for today is to derive the moment generating function for a standard normal distribution and then use a fundamental property of the moment generating function, okay, that is shown here in point 3, and find a moment generating function for the normal distribution. So first we'll derive the moment generating function for standard normal and then for normal. The reason why we're doing this is because probably normal distribution is kind of the key or the most important distribution applied in statistics and also to some extent in finance. The next goal of today's video is to demonstrate this formula here, which is, according to me, one of the most important formula you will ever encounter in your study of statistics. Okay, so let's just state the theory and then we'll do some practice examples. So we start with a random variable x, okay, and this random variable has a moment generating function m subscript x of t. If you have no idea what the moment generating function stands for, go to my previous videos before you proceed with this one. Okay, then what we are doing in point 2, we define a new random variable which is a scaled version or a transformed version of the original x variable. So we are adding a constant here and we are scaling the original x variable by a constant b. Okay, so a and b here are constants. And then once we transform this variable this way, it follows that the moment generating function of the y variable is the same as the moment generating function of the original variable x, but with the constant being now inside the brackets, and also we've got an extra term here. Okay, so you can kind of see that b jumps here inside this bracket and a will go here. Okay, it should become clear in a second what the a and b are. The first thing we usually do when introducing this formula is to prove it, and the proof of this formula in point 3 is actually very easy. So let's recall what the definition of the moment generating function is. It's nothing else but expectation of e to the power ty, where y stands for our transformed variable, yeah, because we started with x, we end up with y. And now what we're doing here in these brackets, well, we just replace y with how it has been defined. It has been defined as a plus bx, yeah. So far so good. Then in this step we are just saying, well, let's multiply a by t and bx by t. So that's kind of standard, multiplication. And here, and we can obviously pull out the EAT term, because as you notice, EAT term is not dependent on x. Okay, expectation is with respect of this random variable x, so we can pull it out in front of the expectation operator. This comes from like basic properties of expectation. You can pull out the constant in front of it. Okay, and so we are left with just this. Okay, well, but what's that? Well, this is exactly the same as the moment generating function of x, which would be defined as expectation of e tx. Well, the only difference being is that we have a b constant here in front of x. So essentially, our y variable will have a moment generating function, composed of the original variable's moment generating function with an extra constant plus, well, times this term here. So wow, we've done quite a lot. We proved that we can get from here to here, or better, from this to this, via this, okay, via that to there, using just simple properties of exponential functions, and obviously the property of expectation operator. Now, before we actually derive the moment generating function of the normal distribution, we still have to obviously get familiar with the formula for the density of the normal distribution, and it looks like this. So you've got here mu is your mean and sigma square is your standard deviation. Okay, the sigma square appears in two places. in the denominator here of this term, but also here in the exponential, in the power of the exponential function. So obviously this is just the density function of the normal distribution. Okay, now what's the difference between normal and standard normal? Well, the difference is standard normal is much more simple to analyze because it assumes that our variance is 1, okay, the sigma square is 1, and the mean is 0. So after applying the change, you will notice that that's what you get here. Right? So that's kind of a reduced version of the normal's distribution density function. Now the question is obviously, how did we get from the normal distribution to the standard normal distribution? What kind of change did we apply to the random variable x such that we ended up with this reduced form, or the standardized normal distribution? What I mean by this, what kind of treatment did we apply to y? Say if y is distributed normally, what kind of treatment do we apply to y to get to x here? X, which is distributed standard norm. Okay, it's very important for us to get this point right. So one more time, we started with a distribution which has a u and variance sigma, mean mu, variance sigma. Okay, so this is a y variable distributed this way normally with this mean and this variance. What did we do to this y variable to get to x, which is distributed with mean 0 and standard deviation of 1? Well, it is a well-known result here on the side. I'm underlining it, highlighting it as we speak, that to get from y to x, we have to take away the mean and divide it by sigma, and we will get our standard normal variable. This process is called normalization. So we normalize the y variable such that we get variable x. Okay, so how do we get from x to y? Because to get from y to x is just y minus mu divided by sigma. How do we get from x to y? Well, it's simple, so we can just rearrange this formula. So y minus mu equals x times sigma. Okay, so now what do we have to do still to get rid of this mu here? Well, we just have to move it on the other side, on the right hand side of this equality. So y equals x sigma plus mu. Okay, so you can switch back and forth between these two variables using these two transformations. One is here and one is here. The thing is, okay, this is what we know because this is what we've been told that we should do to normalize our variable. But say you didn't quite believe, so say you wanted to prove yourselves that this transformation y equals sigma times x plus mu is actually a genuine and valid transformation, and it will get you from x to y. Okay, so let's think of how we can prove it. Okay, so let's see how this can be done. So we started here with a variable, normal variable, with expectation which was 0. Yep, so I'm underlining it here, 0. What's going to happen to our x variable when we add a constant mu? Well, the expectation of x plus mu is just expectation of x plus expectation of mu. Okay, because expectation is a linear operator, so you can, if you add two variables with each other, or a constant and a variable, mu here is a constant, then you can just express it as a sum of two components. Yeah. Now, so because x is a normal variable with mean 0, so basically expectation of x is obviously 0. Now mu is a constant, so expectation of a constant is just a constant, so 0 plus a constant, we are going to end up with a mu. So guess what? That's actually what we wanted, because here we wanted a variable y with a mean mu. Okay, so when we add a constant to our variable x, we indeed end up with a variable whose mean is mu. Great. Well, okay, so how about variance? Variance of a normally distributed variable is 1. Okay, sorry, variance of a standard normally distributed variable is 1. You can see it here as well. Now what's going to happen if we multiply our variable by a constant sigma? Well, okay, so what's the variance of a variable which is transformed this way, which is scaled by this constant sigma? Well, if this is a constant, then it follows from basic property of variance that you can pull the constant out of the brackets in front of the variance, okay, and square it, okay. That's the right transformation. If you want to take out the constant out of the brackets, you must square it, okay. So that's what we've done here. So variance of sigma variance of sigma times x equals sigma squared times variance, okay, times variance, which is the same as sigma squared times 1, because variance of x is 1, okay. So we ended up with sigma squared. So great. So yes, indeed, this transformation, multiplying x by sigma and adding a mu constant, indeed achieves the purpose of transforming the standard normal variable into a normal variable with mean mu and sigma squared for variance. Okay, how about now if we take both the scaling of x and the constant together and try to find out what the mean is of it and what the variance of this is. So let's see if it's going to work. So we defined here y here is equals sigma x plus mu. So what's expectation of the sigma x times mu? Well, there's nothing else as sigma times expectation of x. Yet again, we can pull the sigma in front of the expectation operator, but because we are dealing with expectations, you don't square it, you just leave it as it is. And plus the other term was mu, okay. Expectation of mu is going to be mu. Okay, so what's going to be the expectation of this term here? Well, it's going to be variance stays, and expectation of x, because x is standard normally distributed, it has a mean of 0, therefore the whole thing simplifies to mu. Bingo, okay? So we have proved that indeed y has a mean of mu. Now how about variance? Well, variance is just slightly more complicated, but only a tiny bit. Variance is going to be sigma times x plus mu. So variance of this is just variance of sigma times x plus variance of mu. Why? Well, because this is coming from the standard property of variance. I put here property number 1. If you have a random variable, okay, times a constant plus a constant, you can actually treat it as the sum of two separate terms. Okay, you can say variance of ax plus variance of b. Now, to pull a constant outside in front of the var term, you have to square it. Okay, that's what the property is saying. And variance of b, variance of a constant, is always 0. Therefore, it reduces to a squared times variance of x. So here, okay, we are dealing with exactly the same situation, except for a is sigma and mu is b. Okay, so what's variance of x? So we are here, variance of x will be 1. So if you pull sigma in front of variance, it's going to be sigma squared. So that's why we have sigma squared here. Okay. Yet again, just observe this property here very carefully, and we are just applying it. And obviously, variance of constant is 0, so we have sigma squared here. Okay, so this was just to prove that indeed this transformation y equals sigma times x plus mu is indeed achieving the desired result of transforming our standard normally distributed variable with mean 0 and mu 1 into one variable which is actually normally distributed with mean mu and variance sigma squared. Okay, so now we are fully equipped to tackle our original problem, which was to find out what the moment generating function of a normal and standard normal distribution is. Okay, it was very lengthy introduction, but I can assure you these are the basics, and it will pay off to know how this works in practice, because it will be very useful for subsequent derivation. So now, what is the moment generating function of standard normal variable? Okay, so let's recall the definition of MGF. It's just an expectation of some exponential function, and this exponential function is defined as e to the power of tx. Surprise, surprise, as complicated as it may seem, deriving the moment generating function for a standard normal variable is actually a piece of cake, and you'll be shocked yourselves by a moment that the derivation is so simple, because obviously when you look at the formula of the normal density, it looks kind of scary. Okay, a standard normal density, it looks scary, but we will use some trick such that we will not have to even evaluate this integral to come up with the end result of the moment generating function for a standard normal variable. Okay, so moment generating function is defined as expectation of e to the power tx. Now, how do we find expectation? Well, first of all, we have to put this function here and times it by our density or PDF, probability density function of the standard normal. Okay, and now we of course have to evaluate this integral. But let's look carefully at what we can actually do to simplify this expression. For instance, let's have a look at this bit here. Okay, how did I get to here? Well, all I did was to group likewise terms together. So you've got here exponential function and here exponential function. So if you combine them together, you basically get this from the second bit from this, yeah, and you get tx from the first bit here. Okay, we can do this because this follows from the properties of the exponential functions. Okay, and now the question is, can we do something to this term minus 1 divided by 2x squared plus tx? Can we transform it, or can we factor it, or can we transform it into something that will be easier for us to evaluate? And I put a number 1 here, which refers us to point number 1 over here. It turns out that we have to complete the square, and by completing the square we'll get a polynomial which is much easier to deal with. Okay, it's going to be so easy that we will have our moment generating function of the standard normal variable in like 5 seconds. Okay, so the only tough bit is the completion of this square. It's kind of you just have to apply like a very lengthy formula to get there, but it will definitely pay off. Now, how did I know that I have to complete the square for this expression here? Yeah, how did I know it? Well, unfortunately I didn't. Okay, so this is just a trick, and I read it in a book. Okay, I read it online, and to be frank with you, I probably, if I didn't know the answer, I wouldn't be able to guess it. Okay, like that. You just take it for granted that this trick achieves the desired result. In a nutshell, somebody came up with this idea already, and now I'm just reusing what somebody else has found out. Okay, so how do we complete the square? Well, I'm gonna show you the formula for how to complete the square. It's here. This formula says you've got a times x squared plus bc plus c, which is the same as a times x minus h squared plus k, where h and k are constant. Okay, so here you've got the formulas for both h and k. Here is h and here is k. What this formula is saying, this term, okay, is going to be equivalent to this whole term. Okay, so our the power of our exponential function that we wanted to work with was minus half times x squared plus tx plus 0. Okay, which is the same as a stands here for minus half, B stands here for t. Okay, B stands for t, A stands for minus half, and C stands for 0. So we just express it in the same format as this one here, as the one above. So A here, H we don't know, K we don't know either, but we'll find it out in a second. So these are the formulas for H. Yeah, and H is minus B. So B here is T. So minus B is minus T divided by 2 times A. So divided by 2 because 2 is coming from here, and A is minus half. So 2 times minus half is minus 1. So here the final result is we get minus t in the numerator, minus 1 in the denominator, which equals to t. Okay, so we have found our h. H is t. So therefore we can just plug h, t for h here. Yeah? And then how about k? Well, k is c minus b squared divided by 4a. C is 0, minus b squared, so minus t squared divided by 4 times half. Yeah, 4a, a is minus half. Well, look what's going to happen if we just you know, multiply 4 times 4 times minus half is just going to be 2. Yeah, minus 2. Obviously we've got a minus t squared in the numerator. This becomes a plus, so we have found our k constant. Yeah, so that's why we plugged in this here. So we found our two of our constants, and we can just take this expression and go plug this whole expression into the power of our exponential function. Okay, so take this expression and bring it over here. Okay, so we've got our completed square here. Yeah, this is all this bit here. Perfect. And now let's look carefully. The integration is with respect to x. Okay, x is always variable, so anything that's not x is actually a constant. So you know, when dealing with integrals, you can put a constant in front. So we've got here minus half times x minus t squared, so we can't touch it, we have to leave it. But we've got here plus half t squared, and guess what? We can put this exponential bit, e to the power of half times t squared, in front of this integral, which means that we are only left with this bit here. And guess what? Well, in the first part of the video we learned how to recognize standard normal distributions, but we also learned to recognize how to spot a normal distribution, not just standard normal. So clearly here, okay, so what's variance here? Well, variance here would be always sitting next to 2 and here under the square root. Okay, so what's variance? Well, variance must be 1. Okay, and what's mean? Well, mean is always whatever we take away from x in the numerator here. What's mean here? T. Okay, so therefore it follows that this is a normally distributed variable with mean t and variance 1. And what do we know about valid density functions? Well, we know one thing, that they must integrate to 1. Okay, so therefore it follows that this bit that I'm carving out right now must evaluate to 1. And if this equals to 1, then we are just left with this term here. Yeah, this term here, this is what we are left with. And therefore, hooray, hooray, we finally got there. We derived the moment generating function for the standard normal variable. In the next part of the video we will learn how to apply the formula that we learned, you know, here at the beginning, to derive the moment generating function for normal variable. Okay, now there's a difference, don't confuse. What we just done here, we derived the moment generating function for standard normal variable, and now we'll use the properties of moment generating functions to derive the moment generating function for normal variable, not standard normal, normal variable.